Introduction to Prisma SD-WAN. Welcome to the channel. Please consider subscribing. I produce videos daily covering a wide variety of cloud topics with focus on networking. Also, hit the bell icon to get notified of new videos. In this series we are diving deep into Palo Alto Networks' Prisma SD-WAN, one of the most comprehensive software as a service-defined wide-area networking solutions available today. If you are preparing for an interview, a certification, or you are planning a real-world deployment, understanding Prisma SD-WAN from first principles is essential. SD-WAN stands for Software-Defined Wide Area Network. Traditional enterprise networks connected branch offices to data centers and headquarters using dedicated leased lines such as MPLS, multi-protocol label switching. MPLS is extremely reliable and provides guaranteed quality of service, but it is expensive, slow to provision, and completely inflexible when it comes to adapting to cloud-first workloads. SD-WAN was created to solve those problems. It decouples the network control plane, the intelligence that decides how traffic is routed, from the data plane, which is the actual forwarding of packets. This means the routing decisions are made by a centralized software controller, and the physical transport, whether MPLS, broadband internet, LTE, or 5G, is just a commodity underlay that the SD-WAN orchestrates. Palo Alto Networks acquired CloudGenix in 2020 and rebranded its technology as Prisma SD-WAN. Prisma SD-WAN is not simply a WAN optimization product. It is an application-defined, cloud-delivered, fully autonomous networking platform designed for the modern enterprise where users, applications, and data all live in the cloud. Prisma SD-WAN architecture. Let me walk you through the Prisma SD-WAN architecture diagram in detail. The architecture is divided into three distinct planes: the data plane, the control plane, and the management plane. Understanding these three planes is fundamental to every SD-WAN product and will come up in any interview. Starting with the data plane. This is where actual packet forwarding happens. The ION devices, Intelligent Operations Network devices, sit at branch offices, data centers, and cloud virtual networks. The ION device is the hardware or software appliance responsible for forwarding traffic. It connects to multiple WAN transports simultaneously and implements the policies defined by the control plane. The ION device makes sub-second forwarding decisions based on real-time path quality measurements. The control plane is represented by the Prisma SD-WAN controller, which is hosted in Palo Alto Networks cloud infrastructure. The controller is responsible for computing paths, distributing routing tables, enforcing policies, and maintaining the topology of the entire WAN. All ION devices establish secure tunnels back to the controller. This means no device needs to know the full network topology. The controller handles it centrally and pushes the necessary information to each device. The management plane is the Prisma SD-WAN portal, a web-based dashboard that network administrators use to define application policies, monitor performance, troubleshoot issues, and manage devices. This is the human interface layer. The controller and portal together form what is called the orchestration layer. The key architectural principle here is the separation of concerns. The ION device at the branch does not need to run complex routing protocols or carry the entire routing table. It simply follows the instructions from the controller, which has a global view of the network. This is what makes SD-WAN faster to deploy, easier to manage, and more resilient than traditional routing architectures. Application-defined policies. One of the most important differentiators of Prisma SD-WAN compared to traditional SD-WAN products is its application-aware, policy-driven approach to path selection. This is what Palo Alto Networks calls an application-defined WAN, and it is a concept you absolutely must be able to explain clearly in an interview. In a traditional network, routing decisions are made based on network layer information, specifically the destination IP address and the route with the lowest metric. The network has no awareness of what application is generating the traffic. A video conference call is treated exactly the same as a file backup job. even though these applications have completely different performance requirements. Prisma SD-WAN inverts this model. Application policies are the primary driver of routing decisions. The administrator defines policies that say things like, Microsoft Teams traffic must always use the path with the lowest latency and jitter, even if that path has lower bandwidth. SAP ERP traffic must always stay on the MPLS circuit. Backup traffic can use whatever path has available bandwidth, even if latency is high. To implement these policies, the ION device performs Deep Packet Inspection, called DPI, to identify applications at the session level. The Prisma SD-WAN application database contains thousands of application signatures, covering software as a service applications, unified communications platforms, streaming services, and custom enterprise applications. The DPI engine classifies traffic in real time on the first few packets of each flow, then applies the appropriate policy immediately. The diagram on this slide shows how different applications video conferencing, ERP, and backup are matched to different WAN paths based on their SLA requirements. This per application, per path intelligence is the core value proposition that sets Prisma SD-WAN apart from simple load balancing or basic policy routing approaches. Topology models, hub and spoke versus full mesh. Prisma SD-WAN supports multiple logical topology models that control how branch sites communicate with each other and with the data center or cloud. Understanding these topologies is important both for interviews and for real-world design decisions. The hub and spoke topology is the most common model for enterprises transitioning from traditional WAN. In this model, branch offices, the spokes, connect to one or more central sites, the hubs. The hub is typically the data center or a cloud-hosted virtual ION device. All branch-to-branch communication goes through the hub. This model simplifies security enforcement because all traffic passes through a central point where firewalls and inspection can be applied. However, it introduces additional latency for branch-to-branch communication and the hub becomes a potential bottleneck. The full mesh topology allows any site to communicate directly with any other site without going through a hub. Prisma SD-WAN can build encrypted tunnels between any two ION devices dynamically. These are called on-demand tunnels. When branch A needs to communicate with branch B, the controller instructs both ION devices to establish a direct tunnel. When the communication ends and the tunnel is idle, it is torn down automatically. This provides optimal latency for branch-to-branch traffic while conserving resources by not maintaining thousands of tunnels simultaneously. The partial mesh or regional hub topology is a hybrid that provides the best of both worlds. Regional hub sites are deployed in key geographic locations. Branches connect to their nearest regional hub, and hubs connect to each other in a mesh. This design is common in large enterprises with global presence, as it minimizes latency while maintaining centralized security enforcement at regional aggregation points. The diagram on this slide illustrates all three topologies and shows how the ION devices and the controller interact in each model. Prisma SD-WAN and SASE integration. SASE, pronounced SASE, stands for Secure Access Service Edge. It is an architectural framework defined by Gartner that combines wide area networking capabilities with comprehensive cloud-delivered security services into a single, unified platform. Understanding how Prisma SD-WAN fits into the SASE framework is absolutely critical for any interview at Palo Alto Networks or with any enterprise considering a SASE deployment. Palo Alto Networks delivers SASE through its Prisma SASE platform, which has two major components. The first is Prisma SD-WAN, which provides the WAN connectivity, intelligent path selection, and application-defined routing we have been discussing. The second is Prisma Access, which is Palo Alto Networks' cloud-delivered security platform. Together, these two components deliver the complete SASE architecture. The diagram on this slide shows how Prisma SD-WAN and Prisma Access integrate. Branch offices and remote users both connect to Prisma Access service nodes, which Palo Alto Networks calls compute nodes. deployed in over 100 locations worldwide. These compute nodes provide a full suite of security services including next-generation firewall inspection, secure web gateway filtering, cloud access security broker functionality, zero trust network access, and DNS security. All of this security processing happens in the cloud, as close as possible to the user and the application. Prisma SD-WAN handles the intelligent routing of branch traffic to the nearest Prisma access compute node, ensuring that security inspection does not introduce unacceptable latency. The integration between Prisma SD-WAN and Prisma Access is native. They share a common policy framework, a common identity system, and a common management portal called Strata Cloud Manager. This unified management is a key selling point for the Palo Alto Networks SASE solution. Zero Trust Network Access with Prisma SD-WAN. Zero Trust is a security philosophy based on the principle of never trust, always verify. It rejects the traditional security model where everything inside the corporate network perimeter is implicitly trusted. In a zero trust model, every user, every device, and every application must continuously prove its identity and comply with access policies before being granted access to any resource regardless of where that user or device is located. Prisma SD-WAN plays an important role in enabling zero trust at the network layer. Traditional SD-WAN products provide connectivity but treat security as an add-on. Prisma SD-WAN, as part of the Prisma SASE platform, integrates zero trust principles directly into the fabric. The first zero trust capability is identity-based segmentation. Rather than defining network access policies based on IP addresses or VLANs, which can be spoofed and are difficult to manage, Prisma SD-WAN integrates with identity providers like Azure Active Directory and Okta. This means access policies can say things like users in the finance department on compliant devices can access the ERP application, while contractors can only access the web proxy. These policies follow the user regardless of where they connect from. The second capability is micro-segmentation within the branch. The ION device enforces granular traffic policies between different network segments. For example, ensuring that Internet of Things devices on the branch network cannot communicate with servers or workstations, even on the same LAN. This limits the blast radius of any potential breach. The diagram on this slide shows how user identity, device posture, and application context are all evaluated together before access is granted. The ION device at the branch enforces the resulting policy at wire speed, ensuring that zero trust principles are implemented without impacting application performance. High Availability Design. High availability, commonly abbreviated as HA, is one of the most critical design considerations in any enterprise SD-WAN deployment, and you will almost certainly be asked about it in an interview. In Prisma SD-WAN, HA is not a single feature. It is a layered set of mechanisms that operate at the device level, the path level, and the controller level to ensure the network keeps running even when components fail. At the device level, Prisma SD-WAN supports active-active and active-passive device HA pairs. In an active-passive HA pair, two ION devices are deployed at the same site and connected together via a dedicated HA link. The primary device handles all traffic forwarding while the secondary continuously synchronizes state including active sessions, routing tables, and policy configurations from the primary. If the primary fails, the secondary detects the failure within milliseconds through keep alive messages on the HA link and assumes all forwarding duties. Because the state is synchronized, existing TCP sessions are preserved through the failover event without the end user experiencing a dropped connection. This is called stateful failover. In an active-active HA pair, both devices simultaneously forward traffic. The traffic load is distributed across both devices. If one fails, the other absorbs the full load. Active-active provides both redundancy and additional throughput capacity, making it the preferred design for high-traffic sites. At the path level, Prisma SD-WAN provides HA, through multi-path transport diversity. Because an ION device can simultaneously maintain tunnels over MPLS, broadband, and LTE. The failure of any single transport does not interrupt connectivity. The path selection engine automatically reroutes all flows to surviving transports within sub-seconds. This path level HA operates independently of device HA and applies even in single device deployments. The diagram on this slide shows both device HA and path HA working together to create a resilient branch architecture. Security zones and policy segmentation. Security zones are a fundamental concept in network security that Prisma SD-WAN implements at the branch level. A security zone is a logical grouping of network interfaces or segments that share the same security policy. Traffic within a zone is implicitly trusted. Traffic between zones must be explicitly permitted by a security policy. This zone-based model is much easier to manage and reason about than traditional access control lists applied to individual interfaces. In a Prisma SD-WAN branch deployment, the ION device creates distinct zones for different types of traffic and users. The most common zones include the WAN zone, which represents the untrusted internet and carrier transports, the LAN zone, which represents internal trusted users and devices, the guest zone, which represents visitor Wi-Fi with internet-only access, and the Internet of Things zone, which represents operational technology, printers, cameras, and other devices that should be isolated from the corporate network. Traffic flowing from one zone to another is evaluated against the security policy. In a full Prisma SASE deployment, this interzone traffic is routed to Prisma Access where it undergoes next-generation firewall inspection, URL filtering, and threat prevention before being forwarded to its destination. In a standalone Prisma SD-WAN deployment without Prisma Access, the zone policy can leverage integrated security features on the ION device including stateful firewall, NAT, and basic intrusion detection. The diagram on this slide shows a typical branch security zone architecture. Notice how the IoT zone and the guest zone are completely isolated from the corporate LAN zone. Traffic between them must pass through a security enforcement point. This isolation is critical for compliance with frameworks like PCI-DSS, which requires that payment card systems be isolated from other network segments. From an interview perspective, the key point about Prisma SD-WAN security zones is that they are defined centrally in the management portal and pushed to all ION devices simultaneously. A policy change takes effect across hundreds of branches in seconds, rather than requiring individual device configuration. Deployment modes, controller options. Prisma SD-WAN offers flexibility in how the controller is deployed, which is important to understand for both interview discussions and real-world design decisions. There are two primary controller deployment models: cloud-hosted controller and on-premises controller. The cloud-hosted controller, also called the software-as-a-service controller, is the default and recommended deployment model for the vast majority of enterprises. The controller runs in Palo Alto Networks cloud infrastructure with multi-region redundancy. The enterprise does not need to manage any controller hardware or software. Updates, patches, and capacity scaling are all handled by Palo Alto Networks. ION devices connect to the controller over the Internet using encrypted HTTPS tunnels. This model provides the fastest time to value and the lowest operational overhead. The on-premises controller, sometimes called a private controller, is available for enterprises with strict data sovereignty requirements or regulatory constraints that prohibit management traffic from leaving the country or a private network. In this model, the customer deploys the controller as a virtual machine on their own infrastructure. The customer is responsible for managing the controller, including updates and capacity planning. The on-premises controller supports the same ION device management capabilities as the cloud controller. A hybrid model is also available where the on-premises controller handles local branch management, but leverages cloud-based analytics for visibility and reporting. This provides the data sovereignty benefits of the on-premises controller while still taking advantage of the cloud-scale analytics infrastructure. The diagram on this slide shows how ION devices connect to both controller deployment models and how the management plane traffic flows in each case. One important concept to understand is that the controller handles only management and control plane traffic. The actual data plane traffic between branches flows directly between ION devices through encrypted tunnels and never traverses the controller. BGP and routing protocol integration. While Prisma SD-WAN uses its own overlay routing protocol for SD-WAN path selection, it must also integrate with traditional routing protocols at the edges of the network, particularly BGP, which is the border gateway protocol used for exchanging routing information between enterprise networks and service providers, and between the SD-WAN overlay and existing routing infrastructure. Border gateway protocol integration is critical in several scenarios. The first is multi-protocol label switching handoff. When an enterprise uses multi-protocol label switching transport, the multi-protocol label switching carrier typically delivers the circuit with ACE customer edge to PE provider edge border gateway protocol session. The ION device must run border gateway protocol on its multi-protocol label switching facing interface to exchange routes with the carrier. It advertises the enterprise subnets to the carrier and learns the carrier's summary routes. The SD-WAN controller understands these border gateway protocol routes and incorporates them into the overlay routing logic. The second scenario is data center integration. Large enterprises often have existing MPLS or BGP routing infrastructure in the data center that must interoperate with the SD-WAN overlay. The ION device deployed at the data center can run BGP with the existing data center routers, learning all internal prefixes and redistributing them into the SD-WAN fabric. This allows branch ION devices to reach all data center prefixes through the SD-WAN overlay without requiring manual static route configuration. Prisma SD-WAN also supports static routing for simpler deployments where BGP is not required. Static routes can be configured in the management portal and pushed to ION devices as part of the device configuration. Route redistribution between static routes and BGP is supported, allowing the ION device to advertise statically defined prefixes to BGP peers and vice versa. The diagram on this slide shows how the ION device sits at the intersection of the SD-WAN overlay routing domain and the traditional BGP routing domain, acting as a route redistribution point between the two worlds. This integration point is often a critical discussion topic in advanced Prisma SD-WAN interviews. Licensing and subscription model. Understanding the Prisma SD-WAN licensing model is important for any sales engineer, network architect, or solutions consultant role, and it may come up even in technical interviews when discussing total cost of ownership or deployment planning. Prisma SD-WAN is sold as a subscription-based service. Unlike traditional networking products where you pay a one-time capital expenditure for hardware and perpetual software licenses, Prisma SD-WAN uses an operational expenditure model. You pay an annual or multi-year subscription that covers the software license, cloud controller access, support, and software updates. This shifts the cost from CapEx to OpEx, which is often preferred by finance departments because it avoids large upfront capital expenditures. The ION hardware appliance itself is purchased separately either directly from Palo Alto Networks or through an authorized channel partner. The hardware has no inherent software license. It only functions when a valid subscription is attached to it in the Prisma SD-WAN portal. This means that hardware and software licenses can be managed independently, and subscription renewals or upgrades do not require hardware replacement. Prisma SD-WAN subscriptions are tiered based on the throughput capacity of the ION device and the feature set required. The base tier includes core SD-WAN functionality, multi-path routing, application-defined policies, zero-touch provisioning, and basic analytics. Higher tiers add advanced features like Cloud Blades integrations, extended analytics retention, AI ops capabilities, and enhanced security features. The subscription also includes access to the Prisma SD-WAN management portal and the cloud analytics backend. For enterprises adopting the full Prisma SASE platform, There are bundle licensing options that combine Prisma SD-WAN with Prisma Access subscriptions at a discounted rate compared to purchasing each product separately. These SASE bundles are increasingly common as enterprises recognize the operational advantages of a unified networking and security platform. Competitors and key differentiators. Understanding how Prisma SD-WAN compares to its competitors is essential interview preparation. You must be able to articulate not just what Prisma SD-WAN does, but why a customer would choose it over alternatives like Cisco SD-WAN, VMware VeloCloud, Fortinet Secure SD-WAN, or Ariaka. Cisco SD-WAN, formerly Viptela, is the most widely deployed SD-WAN platform in large enterprises. Cisco's advantage is its massive installed base of existing Cisco networking equipment and the familiarity of Cisco's operational tooling. However, Cisco SD-WAN is known for its complexity. Configuring Cisco SD-WAN requires deep expertise in Cisco's proprietary control plane protocols, including OMP Overlay Management Protocol and vSmart Controller Architecture. The management experience is more complex than Prisma SD-WAN, and the cloud-native SASE integration is less mature. VMware VeloCloud is known for its ease of deployment and its strong orchestration capabilities. VMware's advantage is its deep integration with VMware NSX for data center networking and its large ecosystem of service providers who offer VeloCloud as a managed service. However, VMware's acquisition by Broadcom has created significant market uncertainty, with many customers reconsidering their commitment to the platform. Fortinet Secure SD-WAN bundles SD-WAN functionality directly into its FortiGate next-generation firewall appliances. This integrated approach means every Fortinet SD-WAN device is also a full-featured firewall, which appeals to customers who want to minimize the number of security appliances at the branch. However, Fortinet's SD-WAN orchestration and analytics capabilities are generally considered less mature than Prisma SD-WAN's purpose-built orchestration platform. The primary differentiators of Prisma SD-WAN that you should be able to articulate clearly are the application-defined routing model originating from CloudGenix, the native SASE integration with Prisma Access providing best-in-class cloud-delivered security, the CloudBlade's open integration platform for extensibility, and the AIOps analytics platform that provides proactive rather than reactive network management. These are the reasons a customer would choose Prisma SD-WAN over the competition, and they should be the core of your value proposition in any interview discussion. WAN optimization, FEC and packet replication. WAN optimization in Prisma SD-WAN goes far beyond simple link aggregation or load balancing. Prisma SD-WAN includes two advanced techniques for compensating for poor link quality in real time: forward error correction, known as FEC, and packet replication. Both techniques address the same underlying problem: packet loss on WAN links, but they do so through different mechanisms, and understanding the distinction between them is important for interviews. Forward error correction is a technique borrowed from telecommunications and digital signal processing. When FEC is enabled on a path, the sending ion device does not just transmit the original data packets, it also transmits redundant correction packets calculated from the original data using a mathematical algorithm similar to RAID parity. If one or more packets are lost in transit, the receiving ion device can mathematically reconstruct the missing packets from the correction packets, without requiring any retransmission. This eliminates the latency penalty of TCP retransmission, which is especially damaging for real-time applications, and makes the path behave as if the packet loss never occurred, up to a configurable loss threshold. The trade-off with FEC is bandwidth overhead. Because the ion device is sending additional correction packets, FEC increases the total volume of data transmitted on the WAN link. The overhead is configurable, typically ranging from 25% to 50% of the original traffic volume. This overhead is acceptable for real-time traffic like voice and video, where the elimination of packet loss and retransmission delays is worth the extra bandwidth cost. Packet replication is a simpler but more aggressive technique. When packet replication is enabled, the sending ion device transmits an identical copy of every packet simultaneously across two different WAN paths. The receiving ion device accepts whichever copy arrives first and discards the duplicate. This guarantees that even if one path completely loses a packet, the copy on the other path delivers it successfully. Packet replication doubles the bandwidth consumption, so it is reserved for the most latency-sensitive, loss-intolerant flows, typically voice calls during periods of severe link degradation. The diagram on this slide illustrates both forward error correction and packet replication, showing how each technique adds redundancy to cope with lossy WAN paths. IPv6 support in Prisma SD-WAN. IPv6 support is an increasingly important topic as enterprises face IPv4 address exhaustion and carriers begin offering IPv6 only or dual-stack transport options. Understanding how Prisma SD-WAN handles IPv6 is a sign of technical depth that interviewers will appreciate. Prisma SD-WAN supports IPv6 in a dual-stack configuration. Dual stack means that both IPv4 and IPv6 are simultaneously active on the same interface. An ION device configured for dual stack can receive and forward both IPv4 and IPv6 traffic on its LAN-facing interfaces, and can establish SD-WAN tunnels over both IPv4 and IPv6 underlay transports. This allows enterprises to support IPv6 endpoints in the branch LAN while maintaining full backward compatibility with IPv4 resources in the data center and cloud. IPv6 on the WAN underlay is also supported. When a carrier provides an IPv6 transport, for example a broadband ISP that assigns only an IPv6 prefix to the CPE, the ION device can use that IPv6 transport as one of the paths in the SD-WAN fabric. The SD-WAN overlay tunnels can be encapsulated inside IPv6 packets in the underlay, and the path quality monitoring and SLA enforcement mechanisms work identically whether the underlay transport is IPv4 or IPv6. One important nuance for interviews is that while Prisma SD-WAN supports dual stack in the data plane, the management plane, the connection from the ION device to the Prisma SD-WAN controller, historically operated over IPv4. This is an area of active development, and the current support status should always be verified against the latest Prisma SD-WAN release notes, as IPv6. Management plane support has been progressively expanded in recent software releases. NAT64 network address translation between IPv6 and IPv4 is another relevant capability. When a branch LAN operates in an IPv6 only mode but needs to access IPv4 resources, NAT64 translation can be performed either at the ION device or at a cloud-based translation service. This allows enterprises to transition their branch networks to IPv6 gradually without losing access to IPv4 resources. Prisma SD-WAN and Panorama integration. Panorama is Palo Alto Networks' centralized security management platform. It provides a single pane of glass for managing Palo Alto Networks' next-generation firewalls deployed anywhere in the enterprise, on-premises, in the data center, in the cloud, and at the branch. Understanding how Prisma SD-WAN integrates with Panorama is important for enterprises that already use Palo Alto Networks security products and want to unify their networking and security management. The primary integration point between Prisma SD-WAN and Panorama is through Strata Cloud Manager, which is Palo Alto Networks' unified management portal that serves as the single interface for both Prisma SD-WAN and Prisma Access. Strata Cloud Manager replaced the separate Prisma SD-WAN portal and the Prisma Access portal, providing truly unified management across the entire Palo Alto Networks SASE platform. If you see questions about the Prisma SD-WAN portal in older documentation or training materials, Strata Cloud Manager is its successor. For enterprises using Panorama to manage on-premises next-generation firewalls, for example, at the data center or at large campus sites, The integration with Prisma SD-WAN means that security policies defined in Panorama can be consistently applied to traffic entering the data center from the SD-WAN fabric. The ION device at the data center steers traffic to the on-premises firewall for inspection before forwarding it to internal resources. This creates a consistent security posture across both cloud-delivered and on-premises security enforcement points. Shared object libraries are another important aspect of the Panorama integration. Security objects like application groups, URL categories, and address objects defined in Panorama can be referenced in Prisma SD-WAN security policies through Strata Cloud Manager. This eliminates the need to duplicate object definitions across multiple management systems, reducing administrative overhead and the risk of policy inconsistencies. Real-world deployment scenarios. Understanding how Prisma SD-WAN is applied to solve real business problems is essential for both technical and business-focused interviews. Let me walk through 3 common deployment scenarios that you should be able to describe fluently. The first scenario is the retail chain deployment. A large retail company with 500 store locations is paying for expensive MPLS circuits at every store to support point-of-sale systems, inventory management, and staff productivity applications. The MPLS circuits cost significantly more per megabit than broadband, and provisioning a new store takes 6 to 8 weeks because it requires carrier circuit installation. With Prisma SD-WAN, the MPLS circuit is replaced with a dual broadband internet connection, a primary fiber connection and a secondary LTE backup. The ION device at each store is zero-touch provision. The store manager simply plugs it in, and it downloads its configuration automatically. POS traffic is given real-time priority to ensure card transactions are never affected. The total WAN cost drops by 60 to 70%, and new stores can be connected in days instead of weeks. The entire 500 store rollout takes weeks instead of years. The second scenario is the financial services firm adopting SASE. A bank has a headquarters, 30 regional offices, and 5,000 remote employees working from home. The bank needs to ensure that all traffic, from offices and from home workers, is inspected by a next-generation firewall before reaching cloud applications or internal systems. With Prisma SASE, the regional offices use ION devices for SD-WAN connectivity, while home workers use Prisma Access Global Protect clients on their laptops. All traffic converges on Prisma Access compute nodes for NGFW inspection, URL filtering, and CASB enforcement before being forwarded to its destination. The bank eliminates the need for on-premises firewall appliances at every regional office and dramatically simplifies remote access security. The third scenario is a manufacturing company with OT networks. A factory has both IT networks, for business applications, and OT networks, for industrial control systems and production machinery. These two networks must be completely isolated from each other for safety and compliance reasons. The ION device creates separate security zones for the IT and OT networks, with an explicit deny all policy between them. Only a specific set of applications is permitted to cross the zone boundary. For example, production data flowing to the ERP system. This micro-segmentation is enforced at wire speed by the ION device without requiring additional security appliances at the factory. Security best practices for Prisma SD-WAN. Security best practices for Prisma SD-WAN deployments are a topic that can appear in both security-focused and operations-focused interviews, demonstrating that you think about security holistically, not just as a feature checkbox, shows maturity as a network architect. The first best practice is to always deploy Prisma SD-WAN as part of the full Prisma SASE architecture rather than as a standalone SD-WAN product. Standalone SD-WAN provides connectivity but does not inspect the content of that traffic. When Prisma Access is integrated, all internet-bound and interzone traffic is inspected by a next-generation firewall with full application visibility and threat prevention. This is the most impactful security improvement over traditional branch deployments where internet traffic often bypasses security inspection entirely. The second best practice is to enable encrypted tunnels on all paths, including MPLS. Many network engineers assume that MPLS is secure because it is a private carrier network, but MPLS traffic is not encrypted. If a carrier network is compromised, which has happened in documented nation-state espionage cases, MPLS traffic is readable. Prisma SD-WAN encrypts all overlay tunnel traffic using AES-256-GCM regardless of the transport type, ensuring that traffic is secure even on private carrier circuits. The third best practice is to implement strict zero-touch provisioning security controls. When ION devices are pre-staged in the portal, ensure that the device authentication tokens are single-use and expire after a configurable time window. This prevents an attacker who intercepts a replacement device from using a stale token to register a malicious device into the SD-WAN fabric. The fourth best practice concerns ION device management access. The ION device CLI should only be accessible over a dedicated out-of-band management interface, not over the WAN or LAN data interfaces. Role-based access control should be configured to ensure that only authorized administrators can access the device CLI, and all CLI sessions should be logged to a centralized SIM security information and event management system for audit purposes. The fifth best practice is to regularly review and prune application policies. Over time, application policies accumulate shadow rules, policies that are never matched because the intended traffic has changed or the application has been decommissioned. Shadow rules increase the attack surface and make troubleshooting more difficult. A quarterly policy review process should be established to identify and remove unused policies. Key terminology quick reference. This final slide is your quick reference glossary of the most important Prisma SD-WAN terms and acronyms. Knowing these definitions precisely, without hesitation, is the difference between sounding knowledgeable and sounding expert in a technical interview. Let me walk through each term and explain exactly what it means and why it matters. ION stands for Intelligent Operations Network. It is the brand name for Prisma SD-WAN's physical and virtual edge devices deployed at every site. When someone says ION device, they mean the SD-WAN branch appliance, either hardware or virtual. ZTP stands for Zero Touch Provisioning. It is the process by which a new ION device automatically downloads its configuration from the controller when it first connects to the Internet, requiring no manual configuration by on-site IT staff. DPI stands for Deep Packet Inspection. It is the technique used by the ION device to examine packet headers and payload to identify the application generating the traffic. DPI is the foundation of application-defined routing because you cannot route by application if you cannot identify the application. SLA stands for Service Level Agreement. In the context of Prisma SD-WAN, an SLA profile defines the maximum acceptable latency, jitter, and packet loss for a specific application or traffic class. When a path violates the SLA thresholds, traffic is migrated to a better path. FEC stands for Forward Error Correction. It is a technique that adds mathematical redundancy packets to the data stream, allowing the receiver to reconstruct lost packets without retransmission. SASE stands for Secure Access Service Edge, the Gartner-defined architectural framework that combines SD-WAN networking with cloud-delivered security. Palo Alto Networks implements SASE through the combination of Prisma SD-WAN and Prisma Access. SCM stands for Strata Cloud Manager, which is the unified management portal for the Palo Alto Networks SASE platform, replacing both the legacy Prisma SD-WAN portal and the Prisma Access portal. VION is the virtual form factor of the ION device, deployable as a virtual machine on VMware ES11, KVM, or as a cloud instance on AWS, Azure, or GCP. IOPS stands for Artificial Intelligence for IT Operations, the use of machine learning to analyze network telemetry and provide proactive, predictive insights rather than reactive alerts. Thank you for your attendance. Please consider subscribing to the channel and liking this video.